Okay, here we are, another example problem for angular momentum, 15-109, problem in Hibbeler. It goes like this. An elastic cord has an unstretched length of 1.5 feet and a stiffness coefficient of 12 pounds per foot. That's a force, pounds force. It's attached to a fixed point at A and a block B, which has a weight of 2 pounds. If it's released from rest in the position shown, which is 4 feet away from C, determine its speed when it reaches point C. So determine its speed when it reaches point C after it slides along the smooth glide. So there's no friction along this guide, the smooth guide. And this will be important because it looks like a table, right? Like it's gravity up. It's not, because look at this. After leaving the guide, it is launched onto the smooth horizontal plane. So this is a top-down view. Wow, my pen. This is a top-down view. Determine if the cord becomes unstretched. So the block is restrained by the guide until C, and then no longer. And so the question is, after it comes out, will the cord bring C in or will it not? And so we'll have to think through what would make that happen. And so does it become unstretched? Also calculate the angular momentum of the block about A at any instant after it passes C. So the momentum around point A, that's our center, after it leaves the guide. Okay, so let's look at this. So we need speed at C. So I'll just put VC, speed at C. That's the first thing. And onto the smooth plane. Unstretched. Yes or no? And then angular momentum after C, I'll say. All right, so let's figure out the speed here. So looking at this, the impetus for motion is this stretched elastic cord with this kind of spring constant. So there's potential energy in it due to this stretched spring. And in all cases, it looks like it's stretched from its unstretched length, which is 1.5. So out here it's stretched, I guess it's a 3, 4, 5 triangle. So if this is 3 and this is 4, then this must be 5 by geometry. So stretched to 5 feet, there's some energy in it. And then stretched to 3, there's less energy in it, but still some. So we got to figure that out. So this looks like an energy problem because you got potential energy in the cord, and it turns into kinetic. So let's write that equation down. If I've got initial kinetic energy plus some initial potential energy, that's going to equal the final of each. So what else might be done in this equation that I haven't put in here, right? There might be a sum of non-conservative forces right here. I've eliminated it because there's no friction, and there is work done by the elastic, right? But in this terminology with the potentials, that effect of that force is caught in this potential term. So without further ado, 1/2 of the mass times its initial velocity squared plus 1/2 of the spring constant times the degree it's stretched beyond its unstretched length squared is going to equal, now let's see, there's a 1/2 mv2, that's kind of what we're trying to find, right? Squared plus 1/2 of ks times 3 minus 1.5 squared. All right, so there's a no initial speed. This term is 0. These two obviously can kind of come together here. So let's well, and the halves cancel. Half everywhere. So V2 squared, I'll divide everything by mass, is going to be Ks over m times 3.5 squared minus 1.5 squared. Okay, so let's work that out. So V2 is going to equal the square root of 12 pounds, and we're trying to get to feet per second, so I need 32.2 feet per second squared, and that's going to be divided by the mass. I did that wrong. 12 pounds is a force. It can stay as 12 pounds. It's going to be divided by the mass, which is 2 pounds, and 32.2 feet per second squared times 3.5 squared minus 1.5 squared. All right, that turns out to, we do our units, pounds go away, we end up with, this is, where are my units? How do my units come out on this? Feet per second squared, feet. I lost a unit somewhere. KS, 12 pounds per foot. There it is. 12 pounds per foot. And then so these feet cancel. And then these units are feet squared for those. All right. See, I'd like to stop and point out what I just did. I self-corrected my problem. I knew it wasn't going to be right because the units weren't homogeneous. Always carry your units unless you know without a doubt what they are, and keep them homogeneous so that it works. All right, so this comes out to be 43.95 feet per second. That's pretty dang fast coming out of there. So it's a slingshot and out of there. All right, so what about unstretched versus not unstretched? So we're going to emerge from this guide with this tangential speed here, this angular speed. And the question is, will that rubber band pull it in first? So let's compare the force of the rubber band, which is going to be 12 pounds per foot times 3 minus 1.5 feet. So we're looking at 12 times 1.5, 18 pounds of force that the rubber band, the elastic band, can provide at its current stretch. So we'll just say at 1.5 feet of stretch. And then let's find out what kind of force it takes to overcome. Basically, to overcome it, you'd have to pull in with enough force that it's faster than just to go round, right? Because there's some force that makes it be a circle. So let's calculate the force of just a circle, and that would be mass times acceleration, or mass times velocity squared over rho, which in this case is going to be, there's 2 pound mass over 32.2 feet per second squared. Velocity, pretty fast over here, 43.95 feet squared, second squared. And I got to divide it by the radius. And if it stays at a circle when it comes out of there, the radius will be 3 feet. Okay, so what do my units look like? The feet squareds cancel. The second squareds cancel. We're left with pounds. Good. That's what I want. All right, so 2 times. It comes out to be 40 pounds. 40 pounds of force. So 40 pounds of force to make this a circle is what it would take. The rubber band is providing 18, so no, in fact, this thing is going to open up, right, until such time as that rubber band is providing enough force to keep it on a circular motion. So no is the answer here. No. The velocity was 43.95 feet per second. All right, so last, what is the angular momentum at any point past Charlie? So what is angular momentum? It's the r vector crossed into the momentum, linear momentum. So at this point, it's 3 feet. And right here where it comes off, this is 90 degrees. So conveniently, the cross product just becomes RMV, and then the direction of the angular momentum. Put your right hand, fingers pointing out. Nope, as you were. Right hand, fingers pointing from A, right? It's the R. And then swing them towards the direction of the momentum vector. So in this case, into the page is going to be the direction. So I'll say into. Hibbler sometimes draws these circles to show you, or these curvy arrows to show you kind of the direction. In this case, that would be clockwise. So let's go back to this. 3 feet times 2 pounds over 32.2 feet per second squared. And then the 43.25 feet per second for speed. All right, so this is a smaller number because I didn't square it like I did over here for force. 8.19. So you look at my units, feet cancels, 1 of the seconds cancel. So I have a pound, foot, second. That's because I do the units the way I do. If you do units differently, you can also figure out, it could be, now the number wouldn't be the same, but you could also do this in slug feet per second squared. I'm not going to because I hate slugs, but so there you go. There is your angular momentum. Again, any questions, hit me up. Talk to your friends, read your Hibbler. And I will see you in the Zoom classroom. And again, any questions that you can't solve outside there through your various means, hit me up before class, and I can come better prepared. Thanks.